without a graphing program. Let's see if we can tackle this problem. We want to find the volume of the solid inside of the sphere and outside of the cylinder. And so let's see if we can get a visual of that. We have a sphere. Let's put the sphere here. And the cylinder, the sphere has radius what? 4? So we're looking at a radius of 4. And then the cylinder has a radius of what? 2. So a smaller part over here is this. So if you can imagine, and this is actually one of my Calc 2 questions, and people are expected to try to do this as a volume of revolution. You try to find the area or the volume of the outside. So we start off with a sphere, and then you drill a hole through it, and the hole is a cylindrical hole, and then whatever you have left over is what you're going to try to find in my Calc 2 class. And so it's a volume of revolution of a piece of a circle that's being spun around some axis. That's all it is. It turns out that it might be easier to do this in double integrals with polar coordinates than it is to try to do this in Calc 2 volume of revolution style. So the idea is that we have a surface, we have a solid that's bounded by 2 surfaces, and we have a region on the xy plane. So let's first take a look at the region and then see if we can establish the volume of the 2 surfaces that I was just talking about. So on the xy plane, what is our region going to be looking like? In other words, if you look at this from the top, what image do you see? What? If you look at it from the top, what do you see? Oh, well, the sphere, but what is it? A donut or a washer. It's flat, so it's a washer. Right? So we're looking at a circle of radius 2, which is where the sphere or the cylinder begins, and then we're looking at a circle of radius 4, where the sphere actually is. And it turns out that it's this area here that we're interested in. So this gives us our region, or domain, or whatever you want to call it. And we clearly want to use polar coordinates for this, because trying to use cylindrical coordinates or spherical, Cartesian coordinates. Trying to use Cartesian coordinates would be kind of difficult. So that's this part over here. So now the next question is, what are the 2 functions that are on top and the bottom that we're bounding? So what we have here is a function in the bottom, which is the bottom half of the sphere, and then a function on top, which is the top half of the sphere. Well, this is our sphere. And if we solve for z, we're going to get the top and the bottom half, right? The plus and minus business. So we have z is equal to the square root of 16 minus x squared minus y squared. And then here, for the bottom half, we have z is equal to negative square root of 16 minus x squared minus y squared. So those are the 2 functions, and we would just subtract them. So the top minus the bottom will give us this whole space in between. Okay? Or another approach would be if you just take it from 0 and go all the way to the top and just double it, that would be the same thing, right? It's the exact same calculations that you would do anyways, so we could do that. So we can just say square root of 16 minus x squared minus y squared minus 0, and then double it. Actually, if you minus the negative of that, it'll turn out to be 2 times that anyways. So this is the integrand, and this is our region. Well, let's figure out our region. R goes from where to where? 2 to 4, and theta goes from 0 all the way around to 2 pi. Okay, so we have our limits, we have our integrand. We can set up our integral. We want to change this into polar coordinates. We have an x squared plus y squared, and you'll see this combination. This is minus r squared, 16 minus r squared, right? So this will just be 2 times the square root of 16 minus r squared. That's going to be your integrand. Okay? We'll set up our integral. So the volume is going to equal to, it's going to be a double integral. The inside integral, inside of the integral is going to be a constant 2, 16 minus r squared under square root. And when we're going to integrate with respect to r and theta, remember we include the extra r. This is the extra r that comes from the change of variables from Cartesian to polar. Our r limits go from 2 to 4, and then now we're going to integrate with respect to theta from 0 to 2 pi. Okay? Now, you should be able to do this quite easily by hand, but instead of doing the iterated integral, I see that there are no thetas in here. If there were thetas that I can factor out, I would factor that out. But this integrand in here is independent of theta, right? So I could take this whole expression out of the theta. In fact, I can even take that 2 out. So if I set this up nice and easy, I can almost do this without doing any integrals, except for this last one. But then this last one is just a u substitution anyway, so it's not too bad. So I have a 2. Antiderivative of this is theta from 0 to 2 pi, so that's 2 pi. And then now this big thing that you would integrate, and you can fill that in. Okay? Any questions? So imagine what you would do in Calc 2. You would have a piece of a circle that gets cut off at some point, and you rotate it around an axis, and then you're rotating this area. So the biggest problem that we have in Calc 2 is finding out what your limits are. But we don't have to do it that way. Okay? Any questions? All right, let's do the next one. Where we have a cone and a sphere. So we have a sphere of radius 1. We have a cone. This is the equation of the cone that we know of. Equation of the cone that we probably remember or don't remember is z squared is equal to x squared plus y squared, but then that just means that there's the bottom half of the cone also that we don't need for this particular example, so we don't need to worry about that. Find the volume of the solid above the cone and below the sphere. So if we mark the sphere off right here, then we're looking at the space in between. Okay. Now, if you look at this from the top, which is what we're going to need to do to try to identify your two-dimensional region, if you look at this from the top, what we need to do is we need to see and be able to identify the circle on the xy plane that creates this, that would have been created by the shadow between the sphere and the cone. Clearly should be less than 1, right? Because the radius of the sphere is 1, so it looks like this is going to cut before 1. And so we can do this a bunch of different ways analytically, and one of the ways that we would approach this would be, setting them equal to each other, so to speak. You kind of want the z's put together. It looks like that's one of their combinations. If we take a look at the z here and the z here, maybe we'll do a substitution. Put the cone inside of the sphere, or put the equation of the cone inside of the sphere. So what are we going to get? We do this intersection. We get x squared plus y squared plus z squared is equal to 1, and we're saying that z is equal to the square root of x squared plus y squared. So if you square that, this will be 2 times everything. And then that's just going to make that into 1/2. So here we have x squared plus y squared is equal to 1/2. And so what is our radius here? 1/2? It's the square root of 1/2. Root 2 over 2 or 1 over root 2 or whatever. So that's the radius of the region that we're looking for. Okay. So we'll go with that. We need to set up our limits of integration. Our limits of integration, r is going to go from where to where? From where to where? 0 to 1 over root 2. Theta goes all the way around 2 pi. So we got our limits. Now we just need to figure out the top and bottom functions. Well, the top function is a sphere. And when we describe this in terms of z's, we need to get z by itself. Now, when we solve for z, we have positive and negative, but clearly this is the top half of the sphere, so we're looking at the positive part. 1 minus x squared minus y squared is the top half of the sphere. And the bottom function is the cone, which is the square root of x squared plus y squared. So the integrand, the space in between, is going to be the integrand here. It'll be the difference between those two. So the top function minus the bottom function. Square root of 1 minus x squared minus y squared minus the square root of x squared plus y squared. But we're dealing with polar coordinates, so we want to send this to polar coordinates. And then we're always on the lookout for combinations, x squared plus y squared in here. So for the first one, we have 1 minus r squared. And the second one, we have the square root of r squared. And since r is just all positive anyways, we'll just call it r. So that's your integrand. So we're ready to set up our integral. We got the integrand 1 minus r squared minus r. Let's throw parentheses around that because we're going to multiply this by another r factor. Our r limits go from 0 to 1 over root 2. And then our theta goes from 0 to 2 pi. Okay? So this is another case where it looks like we can separate this to two separate integrals, two integral factors. And so just to take another step, this integral, we should know, if you do it over and over again, it's just going to be 2 pi, right? Integrating from 0 to 2 pi of d theta. So that's one. And then the other one, you'll probably need to split this up. So if I take a little bit of time and distribute that, this first integral will be u substitution. The second integral would be r cubed over 3, and then you evaluate at the limits, and then that's it. Okay? Any questions? Yeah, we did it. Well, we decided to cut it in half and just say we'll just double it. And so we just integrated the top part. All right. So now I don't want to do the last one anymore, so you can figure that out yourselves. Maybe it'll be on the test, maybe not, I don't know. Did anybody do the last one? Yeah. Yeah. Last one's kind of.
I don't know.
Yeah, the last one's kind of fun. Anyways, let's move on. What are we moving on to? This is what happens when I don't prepare for class. I don't have the worksheet and PowerPoint presentation special. All right, we are going to talk about applications of double integrals. So basically the same sort of applications that we might have seen in single integrals, but we're going to focus more on some mass and density mass and center of mass and stuff like that. I sent myself an email. Let me see if I got it. No, I didn't get it. Oh well. I like to stack rocks for fun. You guys do that? That was the picture that I was going to have. Is it 3-point contact? Uh-oh, now this looks like a weird looking face. All right, I guess what I wanted to do is just this. Find a balancing point. When you stack rocks, you have to try to find a balancing point. Now, with rocks and stuff, it kind of has some sort of advantage in that some of the curves can help. It doesn't exactly stand on a point like this, but in general, it's kind of close enough. And so it all kind of depends on the density of the rock. If this is heavier over here, it's a little bit more dense on this side, and then a little bit less dense over here. Then the center of this rock or this plate would be a little bit off to the side where it's heavier. Or is it lighter? I think it's off to the side that's heavier. So what we want to do is we want to focus on that part, or trying to find that center of mass. And we have to be given something to be able to work with this. And so what we're going to be given is we're going to be given kind of like a density function. So the density function is usually the part that's not so practical to get. You know, you're not going to look at the rock and say, oh, the density function of this rock is whatever. That's not something that you think about. But there's some cases where it could be given to you. If you have a plate that you made in your engineering class at Cal Poly or something like that, and then one side is denser than the other. Think about it as like glue on paper. If you don't spread the glue evenly, then the glue is going to be thicker on one side of the paper than the other side or something like that, so it's going to be a little bit denser on one side than the other. There, I think I got my email. I don't really need to do this, but very good. So I just did this the other day. What? And more. Just cover up that funny looking face. Oh, let's make it look flatter. All right, so this is the example that I was trying to go for in terms of balancing the rocks and finding the center of mass that way. So you have to be given a density function to find the precise center of mass. You're given a density function, and the density function, if we're looking at this as a plate, as a flat plate, we can imagine the density function as, let's see, I think they use D or rho. I forgot what they wrote. I'll use D for density. This is the Greek letter delta as a function of x and y. And sometimes this is constant. So if you have a nice, even, flat plate, then everything is constant. And so you would say that this is equal to a constant. If some parts of this plate are heavier than other parts of the plate, then you would have an actual function here that may have both x and y, or maybe just an x, or maybe just a y, but you'll have some sort of combination of things. So that's your density function. So given a density function and the region R that would describe the plate, we can find the mass and you know the physics formulas and stuff. Mass is equal to density times length, or mass equals density times area, or mass equals density times volume, depending on what kind of density you're looking for. Here we're looking for a two-dimensional density based on x and y, so we're looking at mass is going to be the density times the area. And what we're going to do is, technically, we're going to, if we go through this the Riemann sum way, we're looking at little sub-areas. We're going to take this apart into little pieces, and then we're going to take densities of each of those little ones, and then eventually have an infinite number of them, and then it becomes a double integral. So instead of going through all that mess, I'll just go straight to the double integral. So the mass is going to be a double integral over that region. Now the density is the density, and then the area is going to be that sub-area, the little piece of area that we're looking at. So that's it. That's your density. Now, the center of mass gives you the average. When I say average, I mean the mean. I mean mean. The mean along the x and along the y. So the mean, if you guys have ever taken statistics, there's no more stat stuff on the board here, but if you guys have ever taken statistics, the mean is usually denoted by x bar, with a little bar on top. So that's what we're looking at for the center of mass. So we'll continue on. We'll keep this page here going. To find the average x value, x bar. To find the average x value, we're going to do the same double integral. I'm going to save a little bit of room here, so if you're taking notes in pen, or even pencil, I'm going to add another variable in there. It's essentially calculating the center, it's actually calculating the mass, except now for each of these things, we want to see how much the x is contributing in all these little places. So there's an x here, the x variable that we're looking at. I think it's the x. Maybe it's the y. I should check. It's got to be the x. Is it the x? All right. You think so? Yes, it is. I'm sure. I think so. All right. I have my book open. Yeah, it's x. Oh, but it's not quite complete. I have to divide by the m. I have to divide by the mass. All right. So we'll get there. So it is, in fact, the x, and then you want to divide by the calculation that you did for the mass, which at this point should be a constant now. But I'm going to put that whole formula there. So it's 1 over the mass after you've calculated the mass, and then you have to do another integral with an x in there. So that's the average x value. And then the average y value is going to be similarly the same thing, except instead of an x in here, you're going to have a y in there. So over your region R, y times the density function, dA, divided by the mass. Okay, so these calculations help you find what's called the center of mass. And in terms of these stacking rocks, the center of mass would be the point on the rock, the XY point on the rock, that is going to keep the rock balanced. So the center of mass is given by x bar and y bar. Okay? So it's just a matter of, once you know these formulas, it's just a matter of calculating things. So let's do an example where we're actually looking for the center of mass. They ask us for the mass and the center of mass. So let's see. And they have these other formulas too, the moments and stuff like that. You guys can read about that. Let's see, there's one here with a mass and a center of mass. So let's do that. I mean, the other problems would just where you have to find the center of mass, you have to find the mass also. So let's do this one where we have to report both. So we have a shape of the rock or the plate that we're looking at, we're trying to balance, and we have a density function, and that density function is given by this rho. They're using rho. I should have used rho. Rho, which is 23 times the square root of x. Okay, so the first thing we want to do, we always want to do when we're dealing with double integrals, is try to figure out what the region is that we're talking about. So we have a couple of graphs, and we have to find the intersection between those two and then find the boundary. And then somewhere along the line decide whether we're going to use x first or y first. Or if it's polar, then how we're going to set it up in polar coordinates. In this case, we have y is equal to x squared, and x is equal to y squared is a sideways parabola. So I think we have a clear idea of what our region is. And then once we figure out our clear idea of what our region is, we should determine whether we're going to integrate with respect to x2 first or y. It kind of doesn't matter, although how the function, the density function looks like might play into this decision. So let's just, for now, say we're going to integrate with respect to x first, and then if we need to change it, we'll change it later. By the way, am I going to have constant limits all the way around? No. The answer is no. Why are we not going to have constant limits all the way around? Because when would you have constant limits in Cartesian coordinates? What should the shape look like? Square. It has to be a rectangle, a square rectangle. Okay? This is clearly not a rectangular region, so we're going to have constant limits on the outside for sure, but on the inside it's not. So what did I say with respect to x first? So let's draw a line parallel to the x-axis and figure out these functions as functions of x. So I need this green function. I think the green function was x is equal to y squared. That is already x by itself, so that's easy. That's going to be x is equal to y squared. Now the second function here, the top function, the top as in your exiting function, when you're in the region, you're going to exit through this function over here. This function is y is equal to x squared. Now I need x by itself because I'm integrating with respect to x first. And so I would need to rewrite this as x is equal to the square root of y. Now, when I'm doing a square root, when I'm undoing a square of something and I get a square root, I need to consider whether it's positive or negative. Is it positive or negative in this case? Positive. The negative part's over here. So this part over here is x is equal to negative square root of y, which I don't care about because that's not part of my region. I just need to look at the positive part. What are my limits for y? They have to be constant, and so you just need to know where it starts and when it stops. I guess where it starts and where it stops. It goes from 0 to 1, and those are your limits. All right. Now we have to do 3 integrals. One gets us our mass. Second one gets us our x bar. Third one gets us our y bar. So m is equal to, the mass is equal to the double integral over r of the rho function, 23 root x dA. Now, 23 is constant. We can move it out or leave it in. It doesn't really matter. I'm more concerned about how the integral is going to set up. With respect to x, I'm going to go from y squared to square root of y. So I do that inner integral, and then I'm going to do my outer integral with respect to y from 0 to 1. So let's focus on this integral. So let's move the 23 out on the outside. And the antiderivative is going to be x to the 3/2 divided by 3/2 or times 2/3. So 2/3. 2/3 times 23, 60, what? 26, 2/3. No, I multiplied by 3. 3/2. No, I'm lost. What do we do? What? So 23 times 2/3 x to the 3/2. And I'm going to evaluate this y squared and y to the 1/2 square root of y. Yeah, so this is 46 over 3. And then I'm going to put y. If I put square root of y here, this is just going to be y cubed, right? And then if I put y squared here, wait, that's not y cubed, y to the 3 to 3/4. And then now this is going to be y cubed. All right, so that's my function going into this second integral from 0 to 1. We got 46 over 3 constant y to the 3/4 minus y cubed dy. This will be 46 over 3 y to the add 1 7/4 divided by 7/4 or times 4/7. Nothing cancels, huh? Minus y to the 4th over 4. Evaluate from 0 to 1. So if I put 0 in, everything's going to disappear. So let's just put 1 in. 46 over 3, 4 over 7, minus 1/4. Yeah, whatever that is. Let's check our answer, because we can. We got 46 over 3 times 4 over 7 minus 1/4. Anybody work on simplifying this? Yeah, well, I know. Punch in your calculator and change it back into a fraction. Okay. Nobody's going to find it for me? All right, fine, whatever. All right, so that's M. That's your mass. Now let's work on finding our x bar and your y bar. Let's go to the next page for this, since we seem to be out of room. So x bar is going to be 1 over m times your double integral. We already have the integral set up, so let's just write the iterated integral version of this. So, yeah.
46.
Even? Wow. That's nice. So all this stuff cancels after all that, huh? All right. Thanks, Lauren. Now I can change this to 46. And we were integrating, what is it, 23? Square root of x. Oops. A little bit of space here. Because the x bar is going to be multiplied by x. And we integrated with respect to x first, going from y, square, you remember? Y squared to square root of y. And then our dy goes from 0 to 1. Okay? Is it not 46? Too good to be true.
Yeah.
What is it? Do you guys know how to do that in your calculator and get a fraction back? You can literally do this in your calculator, and then there's this button called Math or something where you can change it back into a fraction. All right, so if this is 69 over 14, I need that to be in the denominator, so this will turn out to be 14 over 69, right? The reciprocal. All right, so my integral is going to be pretty close to the same, except I'm multiplying by an x. In this case, it's not going to be that much more work because I'm just going to make this into an x to the 3/2 power, and so on. So can I just put dot, dot, dot here? So the y bar looks like this, and this time your y is constant, so you're kind of carrying on the same sort of calculation for the mass, except when you do the second integral, you multiply everything by y, and so you'll get slightly different results. All right, let me ask you something. Oh, yeah, I wrote that wrong. So we have to keep it the same, and we decided from the beginning that we're going to do dx first and then dy, so that has to be consistent. Now, this is wrong. What's wrong with this if I do it this way? In terms of taking this integral, I have that 14 over 69, and then it looks like I'm just multiplying these integrals, right? So I can take the 23 out. 0 to 1 with respect to y, I take the y out, and then square root of x dx from y squared to square root of y. This is wrong. Why can't I do this when I was doing this before? Because y is in the limits. Because y is in the limits. So I just want to point out that when we were doing these integrals over here, I kind of was moving things around and separating things, right? Why can I do it here? Because what? The limits are constants, right? So the limits are not dependent on the other variables. So that's fine to take things out as long as they're factors and you don't have separate terms or anything. But in this problem, maybe I should use a highlighter. That doesn't work. The y and these y limits, you can't take this y out of this integral because there are y limits that are involved here. Okay? So be careful with doing stuff like that. All right. I won't work out the rest of this. Any questions about the setup? Okay. All right, let's move on to this idea of the average, the mean. Mean is the average. In statistics, we have what's called the density functions. Hey, that's the same as the density function in physics. And so we can find the average kind of like finding the center of mass. So really what we're doing is finding the center of mass, except we just have a different context to it. So let me see if I could just come up with an example. Your homework has one of these, I think. Joint density function. Oh, that reminds me of a cool density function. We'll have to do that at the end. All right, I think we're going to do number 18. So here we have what's called a joint density function, and the idea behind a density function is that if you were to find the area, or in this case kind of like the volume, over all of the real numbers, then it should all equal to 1. So the first question over here is asking if f is a joint density function, and to figure that out, what we want to do is we want to integrate over all of R. Now look at my R here. You see how that's different from the usual R that I've written there? What does this mean? All real numbers? Close. There's a 2 there. The whole two-dimensional plane. On the xy plane, everything in the two-dimensional plane. That's what we're looking at. So everything in the two-dimensional plane of this function and if this whole thing is equal to 1, then you have yourself a density function. And if it's not equal to 1, it's not a density function. So this is supposedly going for an infinite number of ways, right? That's kind of, whoa, that's weird. But we've done improper integrals before in Calc 2, haven't we? You guys have done improper integrals in Calc 2. So this idea shouldn't be far off when you were saying you're integrating over a whole plane. It goes off to infinity. You still get a finite number. That's still possible. All right. So that's what we're going to do. Now, this also gives us a little bit of help here. The fact that this is 0 for a bunch of other places in your two-dimensional plane. So this is equal to some function if x is bigger than 0 and y is bigger than 0, and it's 0 everywhere else. So that kind of trims down our region. It's still going to be an improper integral, I think, but it still at least trims down the region Do you know what this region is going to look like? Two-dimensional plane. What region am I looking at? What? X is bigger than 0. Y is bigger than 0. What is that? That's the first quadrant, right? It's all the first quadrant. So the region that we're looking at, I'm going to call this plane R now. It's just the first quadrant. I don't know what that looks like, the first quadrant. Scribble, scribble. Okay? So if I were to write this, express this as an iterated integral, my iterated integral is going to be going from 0. Well, my function is going to be this function, 0.1 e to the negative 0.5x. I'm going to distribute the negative sign, 0.2y dx. If I integrate with respect to x, I'm going to go from what to what? What? Sorry, I didn't hear you. 0 to infinity. Right? It's all of the first quadrant, so my x is going to go from 0 and never stops. Goes all the way to infinity. And likewise, my y is going to go from 0 to infinity. Okay? Now, I like this function. This actually is a nice looking function because, first of all, I have constant limits. Infinity is a constant. I have constant limits. And so I have something here that looks like it's put together, but if I can split this up to two different factors, I could probably create two separate independent integrals to work with. So do you see that this is e to the negative 0.5x times e to the negative 0.2y? Okay. So we can see that this integrand is e to the negative 0.5x times e to the negative 0.2y. And because of that, I can split this up to separate integrals. So let's see. I'll take the 0.1 out because it's a constant. I'll integrate from 0 to infinity of e to the negative 0.5x with respect to x. I'll figure that out separately from the integral from 0 to infinity of e to the negative 0.2y with respect to y. So I have two other integrals that I think are easier to work with. And we actually need a value for this, so let's do the computation. I mean, let's let Wolfram Alpha do the computation. So it's an integral from 0 to infinity of e raised to the parentheses negative 0.5x, close parentheses. So I'm taking this integral of this thing, and I'm going to go, my x is going to go from 0 to infinity and beyond. So my first integral is going to be 2, it looks like. And my second integral, what do you think it'll be? Second integral is going to be 5. I can feel it. So the second integral is negative 0.2. And I could change this into a y if I want to because it's just a dummy variable. Or I could have just left it as an x. But we want to make it look like the y. So those are our two integrals we did with magic. So we got 10 times 0.1, and that is, in fact, equal to 1. So yes, this is a density function. Okay? All right. Now, the other business over here, let me just point out these things. When they're asking for this P stands for probability. What's the probability that y is going to be bigger than 4, bigger than or equal to 4? So basically what you have here is your y value now starts at 4, and then your region is going to be everything up here, starting from 4 to infinity. Okay? So what this is going to do is, instead of our integral going from 0 to infinity, 0 to infinity, it's just going to go from your x is going to go from 0 to infinity, but your y doesn't start at 0, it starts at 4, and then goes off to infinity. So it'll be the same calculation as above, except your limits will change. Okay? This one says x is less than 7, y is less than 7. So this is 7, and we're looking at less than. So anything that's less than 7 in x and everything that's less than 7 in y. So now I have a new set of limits here. Your x goes from 0 to 7, and then your y goes from 0 to 7. This is 7. Okay? So redo the same thing with different limits. What do you think the expected value is? No. Good guess, though. No. I mean, it could be 1. I don't know. Expected value equals the mean, or x bar. So expected value of x. So that's x bar, and that's just the same formula as the center of mass. X bar is equal to a double integral from 0 to infinity for both x times the function. So it's the same as the other one. Oh, we have to probably divide by the mass, right? Oh, but that's equal to 1. So we don't have to worry about that. So it's just this without the 1 over m, because m, in terms of the mass, is equal to 1 here anyways. So we don't need to worry about that division. So this is just like if we compare it to the center of mass problem that we have, it's exactly the same, except the mass for this case is equal to 1 because it's a density function. All right? Okay, the solutions for the rest of the worksheet will be posted online somewhere, and I'm in the middle of making videos for that as well, so that you can follow through, although we did 2 in class already, so I don't know if that'll help much. All right, so we have a bunch of applications to worry about. The next is going to be, I think, triple integrals. We're going to go into triple integrals now. All right, good luck with whatever you're going to do.